It is 1942 on Warren Avenue on the west side of Detroit, Michigan, inside the Lincoln automobile plant of the Ford Motor Company. The factory floor is a maze of casting equipment, machine tools, and assembly fixtures. And sitting in a corner of the engineering area, gathering dust, are the casting cores and the tooling for an aircraft engine that the United States government has decided it does not want. The engine is a V12, an enormous, sophisticated, all-aluminum 12-cylinder aircraft engine displacing 1,650 cubic inches with 4 valves per cylinder and double overhead camshafts, one of the most advanced engine designs anyone in America has ever attempted. Henry Ford had ordered it built to win a contract to power American fighter aircraft. He had been certain the contract would come. He had spent a fortune on the tooling and the casting cores before the contract was even awarded. And then the contract went to a competitor, and the most advanced engine Ford had ever designed was left with nowhere to go. There is a particular kind of pain in that. Ford had spent enormous sums, had built one of the finest aircraft engines in the country, and had nothing to show for it. The tooling sat idle. The casting cores gathered dust. The engineering investment, one of the largest Ford had ever made, looked like a total loss. And then, in 1942, the United States Army arrived with a different problem. The Army did not need an aircraft V12. What the Army needed, desperately, was a good tank engine, a power plant for the M4 Sherman medium tank that was about to be built by the tens of thousands. The Army came to Ford and, in effect, said this: "We don't need another aircraft V12, but we do need a good tank V8. And the Ford engineers, looking at the idle tooling and the dusty casting cores for the V12 that nobody wanted, realized that they were holding the answer. They would take the V12, cut 4 cylinders off it, and turn it into the V8 the Army needed. The engine that had failed as an aircraft power plant would be reborn as the finest tank engine of the war." To understand why the Army came to Ford, you have to understand the engine problem that was strangling the Sherman tank program in 1942. The standard engine of the early Sherman was the Wright R975 Whirlwind, a 9-cylinder air-cooled radial that had originally been designed for biplanes in the late 1920s. It was not a bad engine, but it was not a tank engine. It was an airplane engine jammed into a steel box. It was tall and wide because of its radial configuration, which forced the rear hull of the tank to be larger than it needed to be. It was air-cooled, which required a massive fan to force air over the cylinders in the enclosed engine compartment. It had a tendency to foul its lower spark plugs, sometimes at the worst possible moment, such as in the middle of a fight with a German tank. And, most critically, every R975 that went into a tank was an R975 that did not go into an airplane, and the aircraft industry was desperate for those engines. The Army knew it needed alternatives, and it pursued several at once. Chrysler had produced the A57 Multibank, 5-car engines bolted together into a 30-cylinder monster. But the Army found it a nightmare to service and underpowered for a 35-ton tank at only 370 horsepower. General Motors had bolted 2 of its 671 bus diesels together into the 6046, but the 671 was itself still being developed, and the Army wanted gasoline engines for its main fleet anyway. None of the existing options was satisfactory. What the Army wanted was a single, powerful, reliable gasoline V8, purpose-fitted to the Sherman that could be built in large numbers. The Army did not have such an engine, but it knew that Ford had spent the previous years developing one of the most advanced aircraft engines in the country, and that the engine was sitting idle because the aircraft contract had fallen through. The Army's insight was that this idle aircraft engine could be the basis for exactly the tank engine the Sherman needed. This is the paradox at the center of the story, and it is a paradox of failure turned into success. Ford had set out to build a world-beating aircraft engine, and it had failed, in the sense that the engine never won the aircraft contract it was designed for and never powered a single airplane in combat. By the measure of its original purpose, the Ford V12 was a complete failure, a multi-million-dollar investment that produced nothing. And yet, that failure became the foundation of one of the great success stories of American tank engineering. The engine that failed as an aircraft power plant, cut down from 12 cylinders to 8, became the Ford GAA, the largest gasoline V8 ever mass-produced, the preferred engine of the United States Army for the rest of the war, and by many accounts the finest engine ever fitted to a Sherman tank. The resolution of this paradox lies in the nature of engineering investment. The work that Ford put into the V12, the advanced design features, the all-aluminum construction, the 4 valves per cylinder, the double overhead camshafts, the sophisticated manufacturing techniques, none of that work was wasted, even though the engine itself failed in its original purpose. The engineering knowledge, the tooling, the casting cores, the manufacturing capability, all of it was transferable to a different application. When the Army needed a tank engine, Ford did not have to start from nothing. It had a fully developed, highly advanced engine design already tooled for production that needed only to be adapted. Cutting 4 cylinders off a V12 to make a V8 is a major engineering undertaking, but it is far less work than designing a new engine from scratch. The failed aircraft engine gave the tank engine a head start of years. The failure was not wasted, it was repurposed, and the repurposing produced something better in its new role than the original engine had ever been in its intended role. The popular history of the Sherman tank, when it considers the engine question at all, tends to focus on the tank's vulnerabilities, on whether it could stand up to the German Panther and Tiger, on the nickname Ronson, and the question of whether Shermans burned more readily than other tanks. It rarely pauses to consider that the Sherman was, by the standards of its weight class, an exceptionally well-engineered and reliable vehicle, and that one of the keys to that reliability was the engine that powered the preferred American variant, the Ford GAA. The GAA is one of the most advanced and most underappreciated engines of the entire war, and its story, the story of an aircraft engine reborn as a tank engine, is almost entirely absent from the popular memory. The GAA deserves better because it was a genuinely remarkable piece of engineering. It was, and remains, the largest gasoline-powered all-aluminum V8 ever mass-produced. It incorporated design features that would not become common in automobile engines for decades: double overhead camshafts, 4 valves per cylinder, an all-aluminum block, a flat-plane crankshaft, central spark plug placement, and an entirely gear-driven valve train with no belts or chains to brake. These were features borrowed from the aircraft engine it had been, features that made it far more advanced than any contemporary automobile or truck engine. The German Maybach HL230 that powered the Panther and Tiger, an engine often described as something special, was in fact neither as advanced nor as reliable as the Ford GAA. The GAA does not get the credit it deserves, partly because it was a tank engine rather than a glamorous aircraft engine, partly because the tank it powered is remembered for its battlefield struggles rather than its engineering quality, and partly because the strange and wonderful story of how it came to exist has simply been forgotten. This is the story of how an aircraft engine that nobody wanted became the best tank engine America built. The story begins with Henry Ford and his desire to get back into the aircraft engine business. In the First World War, the Ford Motor Company had been a manufacturer of the Liberty V12 aircraft engine for the Army Air Service, building these engines at a plant that Henry and Wilfred Leland had originally constructed for that purpose, the same Lincoln plant on Warren Avenue that would later build the GAA. As the 1930s wore on and it became increasingly apparent that there could be a second global conflict, Henry Ford wanted to position his company to win the aircraft engine contracts that a coming war would generate. He anticipated correctly that war would create an enormous market for high-performance, lightweight engines to power fighter aircraft, and he wanted Ford to supply them. The competitive landscape was dominated in the high-performance liquid-cooled aircraft engine field by names like Rolls-Royce, whose Merlin engine was the most illustrious aero engine in existence, and Allison, whose V1710 was the standard American liquid-cooled aircraft engine. Henry Ford's ambition was to build an engine that would surpass these. Some accounts say Ford first sought to license the Rolls-Royce Merlin for American production but could not reach an agreement, and then resolved to build an engine of his own that would be better than the Rolls. Whatever the exact origin, the result was a clean-sheet design, an all-new engine that was not a copy or derivative of the Merlin, despite the campfire stories that have circulated ever since. Ford instructed his best engineers to develop the finest, lightweight, high-performance V12 that money could buy, an engine that would be more advanced and more powerful than anything its competitors offered. And the engineers delivered a design of extraordinary sophistication. The engine that Ford's engineers designed was designated the XV1650. It was a 60-degree V12 displacing 1,650 cubic inches, with an all-aluminum block and head, double overhead camshafts, and 4 valves per cylinder. These were advanced features for the era. Most aircraft engines of the period used 2 valves per cylinder and simpler valve trains. The 4-valve double overhead cam configuration that Ford adopted allowed the engine to breathe more efficiently and produce more power, and it would not become common in automobile engines until the 1980s and 1990s, half a century later. The engine was also designed, unlike the Merlin, for high-volume mass production, using a number of castings in its construction rather than the labor-intensive machining that characterized the British engine. It even featured an exhaust-driven turbo-supercharger in some configurations. It was, by any measure, a technically excellent design, advanced and powerful, and built for production. And it found no buyer. Ford approached the Army Air Corps with a production proposal, so confident of success that the company purchased the tooling and made the casting cores before any contract was awarded, an act of characteristic Ford over-optimism. But the contract did not come. The reasons were not about the quality of the engine. They were about logistics. The competition was the Allison V1710, which had already been in production for some years. There were large quantities of Allison spare parts on hand, and large numbers of mechanics had already been trained to work on the Allison. The newer Allison V12 was an evolution of an existing proven design with an established supply chain and a trained maintenance workforce. The Ford engine, however advanced, was a brand new design with none of that established infrastructure. From a logistics standpoint, adopting the Ford engine would have meant building a whole new spare part system and retraining mechanics at a moment when the existing Allison system was already working. The Army Air Corps chose the proven engine over the more advanced one. The Ford 15D1650 was rejected, not because it was a bad engine, but because it was a new one. And Ford was left holding the tooling and the casting cores for a magnificent engine that would never fly. The salvation of the Ford engine came from an unexpected direction, the Army's tank program. By 1942, with the M4 Sherman entering mass production and the engine shortage growing acute, the Army Ordnance Department was searching for additional engine suppliers to supplement the scarce Wright radial. The Army decided it needed to establish additional tank engine sources, and it looked at what was available in the American engine industry. Ford had a fully developed, highly advanced engine already tooled for production, sitting idle because its aircraft contract had fallen through. The Army recognized that this idle aircraft engine could become a tank engine. The conversation between the Army and Ford has been captured in various accounts, and the gist of it is always the same. The Army did not need another aircraft V-12. It needed a good tank V-8, and it asked Ford whether the company could take its V-12 and turn it into the V-8 the Sherman required. For Ford, this was a lifeline. The enormous engineering investment in the V-12, which had looked like a total loss, could be recovered. The tooling that had been purchased could be used. The casting cores could be put to work. The advanced engine design could find a purpose after all, even if not the purpose for which it had been intended. Ford agreed, and the company's engineers set to work on the problem of converting a 12-cylinder aircraft engine into an 8-cylinder tank engine. It was a substantial engineering task, but it was nothing compared to designing a new engine from scratch, and it could be accomplished quickly, which was exactly what the war demanded. The conversion of the V-12 into a V-8 was conceptually simple and in execution sophisticated. The basic idea was to take the V-12 and remove 4 cylinders, reducing the engine from 12 cylinders to 8, from 1,650 cubic inches to about 1,100 cubic inches. The engineers took the casting cores for the V-12 and chopped off the rear 4 cylinders, retaining the front 8. The resulting engine kept the fundamental architecture of the V-12, the 60-degree V angle, the all-aluminum construction, the double overhead camshafts, the 4 valves per cylinder, the whole advanced design. It simply had 8 cylinders instead of 12. Because the new engine shared the architecture of the V-12, it could be mass-produced with only minor modifications to the existing assembly line, tooling, and castings. The investment in the V-12 was thereby preserved and put to use. Removing a third of the cylinders from an engine is not as simple as it sounds, because an engine is a balanced, integrated system, and changing the number of cylinders affects the firing order, the balance, the crankshaft design, the manifolding, and a dozen other things. The Ford engineers had to redesign the crankshaft for 8 cylinders, adopting a flat plane crank configuration, the same kind of crankshaft that Ford would make a great fuss about decades later when it appeared in the Shelby GT350 Mustang's Voodoo engine, 80 years after Ford had already used it in the GAA. They had to redesign the manifolding, the firing order, the balance, but the core of the engine, the cylinder design, the valve train, the combustion chambers, the aluminum block construction, all carried over from the V-12. The engine that emerged was designated the GAA, and it displaced approximately 1,100 cubic inches, about 18 liters, making it the largest gasoline V-8 ever put into mass production. It was an aircraft engine architecture in a tank engine package, and it brought aircraft-grade engineering to the humble task of moving a 35-ton tank. The finished Ford GAA was a giant by any automobile or truck standard. It was an all-aluminum, 32-valve, double overhead camshaft, 60-degree V8 with a flat plane crankshaft. It displaced 1,100 cubic inches, which is about 18 liters, an enormous figure that dwarfed any automobile engine of the era and remains enormous today. It was physically huge, nearly 5 feet long, about 4 feet tall, and 3 feet wide, and it weighed nearly 1,500 pounds. It was fed by twin Stromberg carburetors, fired by dual magnetos and twin spark plugs in a full dual ignition system, and used cross-flow induction, all features more typical of an aircraft engine than a ground vehicle engine. The factory-rated net output was 500 horsepower at 2,600 revolutions per minute, more power than any other engine ever fitted to a Sherman tank. But the horsepower figure understates what made the engine valuable in a tank. The more important number was torque, the twisting force that actually moved the heavy vehicle. The GAA produced well over 1,000 pound-feet of torque, with peak figures around 1,050 pound-feet, and it produced this torque at very low engine speeds. According to one analysis, the engine could deliver 90% of its torque from as low as 1,000 revolutions per minute. This abundant low-speed torque was exactly what a tank needed. A tank does not need to rev high. It needs to move an enormous mass from a standstill, to climb hills, to push through mud and over obstacles, all of which demand torque at low engine speeds. The GAA delivered that torque in abundance. The 500 horsepower was, in a sense, the engine running at low stress, because the engine's aircraft heritage meant it was massively overbuilt for the tank application. It could have produced far more power with a few modifications. In its tank tune, it was loafing, producing 500 horsepower from an engine that post-war tinkerers would discover could reliably make over 2,000 horsepower with stronger internal parts. The GAA was a sleeping giant, detuned for reliability, and the detuning was exactly what made it so durable in service. What made the GAA special, and what set it apart from every other tank engine of the war, was the aircraft engineering that it carried over from its V12 origins. The engine was built to aircraft standards, with techniques and features that no contemporary automobile or truck engine used. Because of its aircraft heritage, most of its internal parts were safety wired, a technique in which fasteners are secured with twisted wire to ensure they cannot vibrate loose, a standard practice in aircraft engines but overkill, almost luxurious, in a tank engine. Critical components were pinned in place. The engine had no belts and no chains whatsoever. The crankshaft and the 4 camshafts were kept in synchronization entirely by a gear train, which removed the possibility of a belt or chain breaking and destroying the engine. There was a power divider to drive the camshafts, the distributors, and the pumps, all through gears. The combustion chambers reflected the same advanced thinking. The spark plugs were located centrally in the combustion chamber, a feature rare on engines of the time, which allowed for more complete and efficient combustion of the fuel. The 4 valves per cylinder, 2 intake and 2 exhaust, allowed the engine to breathe far better than the 2-valve engines that were standard at the time. The block was a one-piece cast aluminum unit with hardened steel cylinder sleeves, combining light weight with durability. All of these features, the gear-driven valve train, the central spark plugs, the 4 valves per cylinder, the double overhead camshafts, the aluminum construction, were aircraft engine features brought to a tank engine because the tank engine had been an aircraft engine. The GAA was, in effect, a detuned aircraft engine doing tank work, and it brought a level of engineering sophistication to the tank engine compartment that no purpose-designed tank engine of the era could match. This was the silver lining of the failed aircraft program. The failure meant that the Sherman got an engine far more advanced than it would otherwise have received. The GAA went into the M4A3 variant of the Sherman tank, and the M4A3 became the United States Army's preferred Sherman for the rest of the war. The engine was a good fit for the tank, more compact than the tall, wide radial engines, fitting neatly into the engine bay at the rear of the Sherman, which weighed over 71,000 pounds combat-loaded, carried a crew of 5, and mounted a 75mm, or later, a 76mm gun. The GAA gave the Sherman better mobility and battlefield performance than the radial-engined versions, with its abundant torque and its 500 horsepower. And its liquid-cooled aluminum construction made it more reliable than the air-cooled radial engines, which struggled with the cooling demands of an enclosed tank engine compartment. The M4A3 with the GAA engine became the standard model for United States Army use. After some initial development work to resolve the inevitable teething problems of a new engine in a new application, the GAA proved itself to be reliable, durable, and powerful. The Army liked it enough that it decided to standardize on the GAA-powered M4A3 and to phase out the older radial-engined Shermans as quickly as production allowed. Unlike the diesel-powered M4A2 and the multi-bank-powered M4A4, which were largely shipped off to Allies, the GAA-powered M4A3 was the Sherman the American Army kept for itself. The GAA Shermans were not lend-leased to other allies in large numbers, if at all. The Soviet Union may have received one for evaluation, and the British perhaps one as well, but the Army wanted the GAA-powered tanks for its own use and kept them. This was a measure of how highly the Army valued the engine. The diesels and the multibanks went to the Allies. The GAA, the best of them, the Army kept. The GAA's career did not end with the Sherman. When the Army developed its heavier tank, the M26 Pershing, which entered service in the last months of the war, the GAA was chosen to power it as well, in a more powerful variant. The Pershing was a heavier tank than the Sherman, weighing over 40 tons, and it needed a powerful engine. The GAA, with its abundant torque and its overbuilt construction, was up to the task, and it powered the Pershing into combat in the closing weeks of the European War and later through the Korean War. The engine that had begun as a failed aircraft V12 thus powered two generations of American tanks, the Sherman and the Pershing, through the Second World War and into the Cold War. The GAA also spawned a family of related engines. Ford produced variants, including the GAF and the GAA, used in various tanks and tank destroyers, and even circled back to produce a V12 version, the GAC, for heavier applications. All of these engines were produced at the Lincoln plant on Warren Avenue in Detroit, the same plant where Henry and Wilfred Leland had built Liberty aircraft engines in the First World War. There was a historical symmetry in this. The plant had been built to make aircraft engines for one world war, had been converted to automobile production between the wars, and was now making tank engines derived from an aircraft engine for a Second World War. The GAA family represented the full circle of that history, an aircraft engine heritage applied to ground combat vehicles manufactured in a plant that had begun its life-building aircraft engines a quarter-century earlier. The comparison that best illustrates the quality of the Ford GAA is the comparison with its German counterpart, the Maybach HL230, that powered the Panther and the Tiger tanks. The Maybach HL230 has a reputation in the popular history as a sophisticated and formidable engine, part of the general aura of technical superiority that surrounds German tanks. The reality is more complicated. The Maybach HL230 was a capable engine, but it was neither as advanced nor as reliable as the Ford GAA. The German engine was prone to a variety of problems, and the Panther in particular suffered from engine and drivetrain failures throughout its service life. The Maybach was a good engine struggling under the weight of tanks that were too heavy for it, and built under conditions of wartime shortage that compromised its quality. The Ford GAA, by contrast, was an aircraft-grade engine doing tank work at low stress, massively overbuilt, with advanced features and excellent reliability. The all-aluminum construction, the 4 valves per cylinder, the double overhead camshafts, the gear-driven valve train, the central spark plugs, all of these were more advanced than anything in the Maybach. And because the GAA was running at well below its potential output in tank tune, it was under very low stress, which translated directly into reliability and long service life. The popular perception that German tank engineering was uniformly superior to American tank engineering does not survive a close examination of the engines. In the specific comparison of the GAA and the Maybach HL230, the American engine was the more advanced and the more reliable. The Sherman's engine was better than the Panther's engine. This is not what the popular history would lead one to expect, and it is one of the reasons the GAA deserves to be better remembered than it is. The GAA was not available in quantity at the very start of the Sherman program, and this is an important part of the story. The conversion of the V12 to the V8 and the development and debugging of the new engine in its tank application took time. The GAA was a purpose-built solution that had to be developed and refined, and it was not ready in the huge numbers needed during the earliest period of Sherman production in 1942. During those early months, the Army had to rely on the radial-engined Shermans and the other engine variants to fill the gap. The GAA came online in quantity somewhat later, and once it did, it became the preferred engine and the standard for the rest of the war. This timing illustrates a fundamental trade-off that ran through all of the Sherman engine decisions. The GAA was the best engine, but it took the longest to bring to full production because it required real development work rather than simple improvisation. The radial engine was available immediately but was not ideal. The multi-bank was available quickly but was complicated. The diesel was good but needed its own development. The Army in the end used all of these engines because it needed tanks immediately and could not wait for the perfect engine to be ready. The improvised solutions filled the gap while the better engine was developed, and once the GAA was ready, it became the standard, displacing the improvised solutions for American use. This is how the war was actually fought, with a mixture of immediate improvisations and longer-term proper solutions, the improvisations carrying the load until the proper solutions arrived. The GAA was the proper solution, and it was worth waiting for, but the war could not wait for it entirely, which is why the Sherman had so many engines. When the war ended, thousands of Ford GAA engines entered civilian life, and it was in civilian hands that the engine's true potential was discovered. Because of its extreme reliability and its abundant low-speed torque, the GAA was ideal for industrial applications, and surplus engines found their way into oil field equipment, into trucks, into boats, and into agricultural machinery. The engine that had been built to fly and had instead gone to war in a tank settled into a long and productive civilian career, powering pumps and generators and heavy equipment, running at the low, steady speeds for which its torque characteristics were perfectly suited. And then the tinkerers got hold of it, and they discovered just how much potential the engine had been hiding. In its military tune, the GAA produced 500 horsepower, but this was a small fraction of what the engine was capable of. The aircraft-grade construction meant the engine could handle far more power than it had ever been asked to produce. Hot rodders and racers discovered that the stock GAA could be pushed to around 1,200 horsepower before the piston rings began to fail, and that with stronger pistons, better valve springs, balanced components, and the addition of a turbocharger or supercharger and direct injection, the engine could produce a sustained, reliable output of 2,200 horsepower, more than 4 times its military rating. The legendary racer Art Arfons built a GAA for use in a Bonneville Salt Flats race car. The engine that had been detuned to 500 horsepower for reliable tank service turned out to have over 2,000 horsepower of untapped capability, a measure of just how overbuilt and how advanced the original aircraft design had been. The GAA's post-war career as a hot rod and racing engine revealed the true magnitude of the engineering that Ford had put into the failed aircraft V12 all those years before. There is an interesting historical might-have-been buried in the GAA story. After the war, with all the tooling and engineering already in existence, Ford could, in principle, have scaled the GAA design down to automobile size, to perhaps 300 cubic inches, and put its advanced features, the double overhead cams, the 4 valves per cylinder, the aluminum construction, into a passenger car engine. The basic design was already proven. It would have been a matter of scaling the existing architecture down. Such an engine would have been decades ahead of its time, anticipating the advanced automobile engines that would not become common until the 1980s and 1990s. Ford did not do this, and the reasons reflect the economics of the post-war automobile industry. The advanced features of the GAA, the gear-driven valve train, the double overhead camshafts, the aluminum construction, were expensive to manufacture. The gear-driven camshaft assembly in particular was probably the least efficient part of the engine to produce, and it could have been replaced with a much cheaper chain drive for an automobile application. The post-war American automobile market was driven by cost, by the need to produce engines cheaply for mass-market cars, and the sophisticated, expensive aircraft-derived features of the GAA were not suited to that market. American automobile engines of the post-war era were simple, cheap, pushrod V8s, and that was what the market wanted. The advanced engineering of the GAA, perfect for an aircraft engine or a tank engine where performance and durability mattered more than cost, was economically unsuited to the mass-market automobile. So the GAA's advanced features went back into storage, in a sense, not to reappear in mainstream automobile engines for another 40 years. The engine remained a magnificent oddity, too advanced and too expensive for the market that might have used its descendants. The lesson of the Ford GAA is a lesson about the value of failed projects, about how engineering investment is rarely wasted, even when the immediate goal is not achieved. Ford set out to build a world-beating aircraft engine and failed to win the contract. By the narrow measure of its original purpose, the V12 program was a failure, a large investment that produced no aircraft engine. But the investment was not wasted. The engineering knowledge, the advanced design, the tooling, the manufacturing capability, all of it was transferable, and when a different need arose, the failed aircraft engine became the foundation of a successful tank engine. The failure became the success through repurposing. This pattern recurs throughout the history of technology. The thing that is developed for one purpose turns out to be perfect for another. The investment that looks wasted turns out to be the foundation of a later triumph. The Ford GAA is a particularly clean example because the path from failure to success is so direct. The same casting cores, the same tooling, the same basic design, cut down from 12 cylinders to 8, went from rejected aircraft engine to preferred tank engine. The lesson for anyone who works in engineering or in any field where ambitious projects sometimes fail is that the value of a project is not always realized in its original form. The capability built, the knowledge gained, the tools created can find unexpected applications. Ford's failed aircraft engine became one of the great tank engines of the war, and the failure, in retrospect, was simply a detour on the way to a different and equally valuable destination. The engine that could not get a job flying found a better job fighting on the ground. By the later part of the war, the Ford GAA had become the standard engine for the American Sherman, displacing the radial and securing its place as the power plant of choice. The M4A3 with the GAA was the Sherman the Army wanted, and it produced as many as it could and converted its fleet toward the GAA-powered standard. After the war, when the Army drew down its tank fleet and decided which Shermans to keep, it kept the M4A3 with the 76mm gun, the GAA-powered model, and over time it upgraded as many of these as possible with improved suspension. The GAA was the engine the Army trusted, the engine it kept, the engine it carried forward into the post-war years. The GAA's reputation among those who know tank engines is high. It is regarded as one of the finest tank engines of the war, possibly the finest in its class, more advanced and more reliable than its German counterparts, and superior to the other engines that powered the Sherman. The Sherman Tank Site, an authoritative source on the vehicle, describes the GAA as the best of its type for a long time to come, if not ever, and as really a much better motor for a tank in the Sherman's weight range than the radial it replaced. This is a strong judgment, and it is deserved. The GAA brought aircraft-grade engineering to the tank, and the result was an engine that performed superbly and lasted. The failed aircraft engine, reborn as a tank engine, became the standard against which other tank engines of its era are measured, and it stands up to the comparison better than almost any of them. In a war decided by what worked was a failed aircraft engine cut down into a tank engine. Henry Ford had set out to build the finest aircraft V12 in America, and he had succeeded in building a magnificent engine and failed to sell it because the Army Air Corps wanted a proven engine with an established supply chain rather than a brilliant new one. The tooling sat idle. The casting cores gathered dust. The enormous engineering investment looked like a total loss. And then the Army's tank program arrived with a different need, and the failed aircraft engine became the answer. 4 cylinders came off the V12, and the Ford GAA was born, the largest gasoline V8 ever mass-produced, an aircraft engine doing tank work more advanced than anything its competitors fielded. The GAA carried aircraft-grade engineering into the tank engine compartment. The safety-wired internals, the gear-driven valve train with no belts or chains to break, the central spark plugs, the 4 valves per cylinder, the double overhead camshafts, the all-aluminum construction, all of it came from the aircraft engine that the GAA had been. And because it was an aircraft engine detuned for tank service, running at 500 horsepower when it was capable of over 2,000, it was under low stress, massively overbuilt, and supremely reliable. It powered the M4A3 Sherman, the tank the American Army kept for itself while it shipped the diesels and the multibanks off to its allies. It powered the M26 Pershing into the Cold War. It outlasted the war as an industrial and racing engine, and it revealed in civilian hands the over 2,000 horsepower of capability that Ford had engineered into it and the Army had never needed. In a war fought between industries, the industry that could turn a failed aircraft engine into the best tank engine of its class was the industry that won. The Germans had the Maybach, a good engine struggling under tanks that were too heavy for it. The Americans had the GAA, an aircraft engine loafing along at half its potential in a tank that suited it perfectly. The Germans' engine was special, the histories say, but it was neither as advanced nor as reliable as the engine that Ford built from the wreckage of its aircraft ambitions. The GAA was not in any Hall of Fame. It was a tank engine, born from a failure, remembered by enthusiasts and forgotten by everyone else. But it was the best of its kind, and it carried the American Army through the war and beyond. The aircraft engine that could not fly found a better life on the ground. It started every morning, it pulled the tank all day, it made more torque than anything else in its class, and it was so overbuilt that it could not be broken. In a war decided by what worked, the engine that failed as an airplane worked as a tank. That was enough. It was, in the end, the finest engine the Sherman ever had. Timeless. During World War II, the Henry Ford Aircraft Factory at